this video should pretty much wrap up what we're doing, I think. We're going to talk today about volume. Loud noises and very quiet noises. And if you notice, loud noises have a lot of energy in them. Whereas quiet noises do not have a lot of energy in them. And one way we measure volume is using the intensity. Okay, so intensity is related to volume, and it's also decibels. You know, the Seattle Seahawks just broke the world record for the decibel reading created by a crowd. It was like 130 something. I should probably look that up. Or you look it up. You look it up. What is the world record for the loudest crowd noise? Because the Seattle Seahawks just did that this last season. So like we said, the loudness, the volume, is a measure of the amount of energy, and so what it does is it increases the amplitude of the wave, and that's the important thing to remember. Energy is related to the amplitude. So you know, a little tiny wave like this doesn't have very much energy in it, whereas a big wave like that has a whole bunch of energy. Our loud noises have higher amplitudes, and that means our particles are vibrating with greater pressure differences. So when those guys hit your eardrum, okay, a loud noise has a high pressure, which makes your eardrum go way out that way. And then it has a low pressure, which sucks your eardrum back out that way. And your eardrum's vibrating with super high pressures and super low pressures. And that's what causes the tearing in your eardrum that hurts when you hear super loud noises. And so our louder sounds, oops, we got rid of that on accident, have more power. Because remember, power is our energy per unit time. So if we have more energy, we have more power. And so the way we record intensity is power per square meter. So intensity, the units for intensity are power, which is watts, per square meter. So when you see that, you know you're kind of talking about how much energy it's carrying and its energy, but this will help us calculate how much power a source had originally. So we said our intensity is our power per, our watts per area, per square meter. Okay, area, square meter. Here's what's happening. Okay, so we make a noise, and that noise radiates out. Okay, but remember, it's radiating out 3D, so it's also coming towards you and away from you, so it's making a giant sphere. So that area that we're talking about here is the surface area of the sphere. So really our intensity equation will come out to look more like intensity is our power divided by 4 pi r squared. 4 pi r squared is the surface area of a sphere. Okay, so this brings us to the inverse square law, where the intensity is proportional to the inverse of the square of the radius. So if I'm sitting, you know, here's Mrs. Mack, she's flapping her gums, talking, la 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 la, and you're sitting right here, 1 meter away, and the back row people are sitting back here, 3 meters away. Okay, inverse square. So the distance from me is 3 meters. You're going to take that distance and you're going to square it. So a person 1 meter away and a person 3 meters away, a person 3 meters away is going to hear 1/9 of the intensity of a person that is 1 meter away. So that's why as you get further and further and further away from people, you notice that you can hear them less and less and less. And then as you get closer, oh, all of a sudden you can hear them. It's because it's proportional to the square. So this whole inverse square law idea is one of the things we want to have. Now the unit for volume is decibels, and that's kind of a ratio of intensities. And really, the way you calculate decibels, okay, deci, okay, so it's a tenth of a bell. I don't know why they made decibels instead of just bells, but they did. So it's 10 times the logarithm, so it's a log thing. That's going to be important in just a minute. Of the intensity divided by the threshold of hearing. Okay, so the smallest sound that we can hear is 1 times 10 to the minus 12 watts per square meter. And so that's a constant. I mean, that's just what we use. Yes, there are people that can hear quieter, and yes, there are people that can't hear that. But that's what we use as a baseline for the decibel reading. That is the quietest sound that you can really hear. Okay, so regular physics, you need to know it's a log thing. Honors physics, you need to be able to calculate using this whole equation. But here's the important thing. Okay, it's a log thing. Okay, remember logs, and you may or may not remember this, but logs mean basically to what power is the 10 raised. Okay, so if I have one sound that's 10 to the minus 10 and another sound that's 10 to the minus 8, okay, there's a difference of 100 here. But the difference in the exponent is only 2. So this is very much like the pH scale that you saw in chemistry, where if you went up by 2, if you went from a pH 2, I can write, you went from a pH 2 to a pH of 4, that was a difference of 100 times. Okay, same thing, except for, remember we have this 10 in front. So when we go from a decibel reading of 20 to a decibel reading of 40, that means it's 100 times louder. You have 100 times as much power. If you go from, let's say instead of going from 20 to 40, let's say we went from 20 to, I don't know, what, 60. Let's say we went to 60. Okay, here's the easy way to do it. Kind of ignore the zeros, because you're going to divide by 10. Remember, in the decibel equation we have 10, so we're going to ignore the zeros. That we basically divided it out. And this is the difference in the exponents. So we're going from 10 to the second, okay, because remember log means to what exponent is 10 raised, to 10 to the 6th, okay? That's a difference of 10 to the 4th. That's 10,000 times louder. Okay, so you're starting to see how this is an actual log scale thing. So it's not just, you know, if you looked at that, you might be tempted to say 3 times louder, because going from 20 to 60 you multiply by 3. But you need to remember that it's a log thing, and so the 2 and the 6 refer to the exponents on our 10s. Spit it out. So the 2 and the 6 refer to the exponents on 10. So you have a difference of 10 to the 4th, 10,000 times louder. And that'll be it for regular physics. Honors physics, rock on, keep going.